Good morning, everyone. Thank you for joining us, and welcome to Teledyne ISCO's November webinar focused on what flow technologies work where others won't. Today's presentation is being led by Rick Dye, our Global Key Accounts Manager. If you have questions or comments during the webinar, please utilize the chat function within the Zoom platform. All questions will be answered at the end of the presentation. At this time, I will turn it over to Rick.
Thanks, Tori. I'd like to welcome everybody today. This is another record crowd in attendance, so we appreciate everybody taking the time out of their busy schedule to attend our webinar. This is one of a series that we've done. One was just presented a couple weeks ago by Daryl Kuda, and it discussed more on different flow technologies and where they're used. This is going to be a little bit more focused on application stuff. So anyway, welcome feedback from you at the end of this and what you would like to see maybe going forward. So let's go ahead and get started. This is the ISCO Flow Measurement Lab. Some of you have been to the facility and have seen this, but if you haven't, this is one of the really nice features, I think, behind the facility here. We can use a 4-inch up to 24-inch pipes. Flow ranges up to 2,800 gallons per minute. What this has done for us is we've developed all of our area velocity technology on this facility. And this has been very, very useful. It helps us simulate a lot of different hydraulic conditions, as well as what happens if I dam up the flow, what happens if this happens. So we are able to really do a lot with design work, but we also use it a lot for future enhancements and improving performance of all our technologies. A lot of you have used the 2150 area velocity meter out there. We made a lot of changes since the release of that in '99 and continuously try to improve. The laser is the same way. We've made some improvements on that since the first generation was released in 2013. So excellent facility, and if you ever come to Nebraska, I'd be happy to give you a tour. All right, so let's talk. Today we're going to be talking about area velocity flow measurement. We're not going to be talking about flumes or weirs, but focus mainly on this. So let's talk about that. Q is your flow is equal to the area of water. We find the area by doing some sort of a level measurement. We'll either use a pressure transducer. In the case of a 2150, we use a pressure sensor, but you can also use ultrasonics. Ultrasonic sensor, there's a couple types. One is a downward looking, and you can also have an underwater upward looking ultrasonic to measure that level. V is the velocity component. The most common way of measuring velocity is using Doppler or a Doppler shift. There are either contact sensors, and by contact I'm referring to one that's on a band that's in the pipe. Non-contact would be just as it implies, not in the flow, and that would be what the laser will do. So let's kind of give you a little visual of what a sensor looks like when it's the traditional one. There's a sensor on the bottom of the pipe, and it's measuring the level using a pressure sensor. It transmits an acoustic signal out the nose to measure the Doppler shift. We know the frequency transmitted, we know the return frequency, and we can calculate the velocity. These are very, very popular in the industry, mainly for inflow and infiltration studies. There are thousands of these in service. But not all products are going to work in every application. And that's one thing I think we do pretty well is we have a lot of product offerings depending on your particular application. So again, not all works in every application. We need to pick and choose. One thing I think we have a pretty good handle on is what applications to be used, which technologies to be used in which application. So we have a very trained application staff at the factory to help you, as well as an extensive rep and distributor network. So let's talk about the right product for the application. This is the LaserFlow. The lasers now coming out of the factory are blue in color. We made that change because we will soon, after the beginning of the year, be releasing the LaserFlow EX, which will be an intrinsic safe laser. That will be the black color. So all non-IS lasers or EX lasers will be blue. So we will have more on that as we get closer to release. So So let's talk about the theory of operation of the laser. There's two main components to the laser. One is an ultrasonic sensor, and it is mounted in the back of the laser. It transmits a signal, reflects off a deflector plate, hits the surface of the water, knows where the water is. Once it knows where the water is, we focus the laser below the surface. So we take a measurement to know where the water, we focus the laser, and that's where we get our signal back. This is the patent of the laser. Before we get into the laser, let's talk about the principles of operation of the ultrasonic. The ultrasonic is mounted again in the back of the sensor. When we designed this, we talked to a lot of customers, and this was one of the recommendations that they had was to mount it at an angle. And the reason we did that is so the moisture, whether it's recovering from submergence or just humidity in the environment, will just drip off that laser, the ultrasonic face, so we will not have to clean it. It has a built-in deflector plate, which is built into the molded body housing. It reflects off of that and transmits and hits the water. The other key thing about it that we took into account was the dead band. Every ultrasonic pretty much has a dead band. Normally they're 12-inch. This is similar to this one, 12-inch dead band. With the design, we've accounted for that 12-inch in the housing. So now we have virtually a zero deadband sensor. The water can go all the way up, and including submergence, before it will quit reading level. The laser has a 10-foot range, so it can be in a dry pipe 10 feet above the minimum flow. Okay, let's talk about the operation of the laser. A traditional laser pointer has a fixed focal point. The magic behind the laser is how we focus the laser. So we have optics in the laser itself. We know where the water is, and we focus that laser to get a very defined area that we're looking for the velocity. That area that we focus on will give us our maximum reflected intensity or light from the laser signal. We know the frequency transmitted, we know the frequency returned, and we can calculate the Doppler shift and thus the velocity. So here's kind of a front view, side view of a laser. So here's we're reading the level, we know where it's at. We focus the laser below the surface of the water. And at that point, that is known as what we call the converging section or point of convergence. And what we're doing at that point is getting a lot of signals back. Matter of fact, 5,000 velocity scans or readings in about 2 seconds. So it does a lot in a very, very short amount of time. So incredible. For those of you that may have been involved in the first generation laser, this reading took roughly 45 seconds. So again, on the improvement philosophy, we've continued to refine some of the firmware things as well as the performance of the laser, and this is one area that we've done that. Okay, so why does the laser work so well? Well, the signal to noise ratio is incredible on the laser. So this peak that you see here is the signal, return signal from the 5,000 velocity scan. On the bottom scale, that is your velocity, but it's in frequency. So to the right is faster velocity, to the left is slower velocity. As the speed of the water changes, that signal will move back and forth along that scale. The key thing about this is that our noise level is really, really low. So what that means to you is that the laser will read extremely slow velocity as well as very clean water. So first generation laser, we had a lot of noise at the low end, so our minimum velocity was 0.8 feet per second. We can now read much, much slower velocity than that. This is known as a reading called Doppler power, which is really a measurement of the quality of the velocity reading. A couple things make up this reading. One would be particles in the water. We typically need something to read, although in the case of laser, the signal is so clean that we need minimal particles. But it's also related to the hydraulics. So this tells me at a quick glance that my hydraulics in this line are pretty good. I have plenty of stuff to reflect off of, and the laser likes what it sees. So all is well here. This is stored again as Doppler power, and Doppler power, we need a minimum of 1,000 as a reading. So you can graph your level and velocity and flow, and as well as Doppler power. So you can pick out a point and say, yep, my reading was good, and here's why. So some really good diagnostic stuff available. All of Teledyne ISCO's flow measurement technologies have pretty extensive diagnostics capabilities. The laser is no different. The laser has a built-in accelerometer. What that does is that tells you the angle of the roll and the pitch of the sensor. But this is what we're really looking for. This is a actual application where we can look online and we can see, yep, my laser is still working great. I have a real good return signal. Everything agrees on the reading coming back, so I'm confident in my reading. The XY angles, that is the accelerometer portion of this. X should be 0 plus or minus 3, that's the roll, and it's 0.07, so it's right on the nose. Y should be 45 plus or minus 3, it's 44.5. So that tells me a couple things. The installation was nearly perfect. If the thing ever went underwater and what became submerged and the water receded, this tells me that nothing moved. The laser mount held, and based on that signal there, it tells me we don't have to go in and do anything. So you don't have to clean it, you don't have to touch it. So really, really good diagnostics information. So how do we run this thing? Well, we can set it up a couple different ways. One way, we do a ultrasonic level measurement. We know where the water is. We can do single point, multiple points, or any combination of those. So in this case, we're doing a full 15-point spread, which is known as a multi-point, multi-depth velocity method. When you look at these, each one of these readings in this diagram represents 5,000 velocity readings. So when you do this, you're getting, if you get all 15, you're getting about 75,000 velocity readings in roughly a minute and a half. By comparison, a standard area velocity typically takes up roughly 512 readings. So a lot goes on, a lot of processing power in that meter and that sensor, and a lot of very detailed velocity analysis. This is what the grid looks like. So for those of you that may have programmed or used 2150s, looks very, very similar to this. The difference is on the velocity screen, you can pick and choose which velocity points you want to look at. In this case, we picked the first one, the middle one, and the far right one. This was a site in Canada. It's in meters per second, but you can see it's 4.2 meters per second. That water is cruising and moving very, very fast through that channel. In this case, the laser was the only thing really that they could even put in the flow. All right, let's talk a little bit about accuracy. Now that we have a lot of experience with the laser, we've done a ton of field tests, or we haven't, but a lot of customers have. They've been compared to multiple standards, industrial standards, such as flumes, magnetic flow meters that are very common in the industry, acoustic Doppler flow meter, ADFM. Some of you may remember that from the MGD days. Transit time, multipath transit time, which are very accurate meters, weirs, dye dilution, and so on. So a lot of field tests have been done to compare the laser. We will be coming out with a document in the not too distant future describing some of the accuracies and the tests that we ran. So lab tests, a lot of laboratories have tested these as well. And a couple that we worked with I'll list here in a minute, but our current published specifications are 4% of reading. So we are the most accurate non-contact technology available on the market. We confirmed this by third-party testing. The one facility we did, which is Irrigation Training and Research Facility in Cal Poly San Luis Obispo, we were 1.8% absolute error, so did really, really well in their test facility. There's another lab on the East Coast known as Alden Research Lab, which is a very well-respected lab. They tested the laser, found it to be 2.7% absolute error. So we did really, really well in those accuracy third-party testing. So field tests confirm it as well as the lab tests. So let's talk about some difficult applications. High velocity, low level. One of the top difficult ones, typically due to steep slope pipes. Duluth, Minnesota, I mean, you name it. There's a lot more out there than I thought there was. But low level, high velocity is very, very challenging, if not impossible to measure with a traditional in-pipe sensor. Low level raw water, wastewater velocity. That's always challenging because a lot of times your water goes below 1 inch. Well, in the case of most area velocity, 2150, we get readings above 1 inch and then we interpolate below 1 inch, but it's semi-made up data because it can't read less than 1 inch. The laser can read much lower level than that. Slow velocity, another really challenging application, and that's typically anything less than about a ½ foot per second. Residential collection systems, you'll find low velocities. When you have these kind of conditions, the other thing will happen is obviously you have stuff settling out and covering sensors. When that happens, they're just not going to read. So slow and clean moving water is another challenging one. Wastewater effluent plants, very clean, hopefully if they did the job right, and a lot of times not a lot in there to see. Chlorine contact and UV disinfection channels, another big one that's popped up on the radar. So a lot of times they want to monitor the UV channels to know how to dose or pace their lights. Drinking water to plants, open channel drinking water. We did one down in Kansas, and it was 20 foot wide. They put 2 lasers to kind of span that 20 foot width, and it's water coming into the drinking plant. So stormwater, another one that is becoming very popular. Why is that? Well, they need to measure that. There's a wide fluctuation in flow conditions. You're going to go from dry pipe to, who knows, 10 foot deep water. A lot of irregular shaped channels as well. So a lot of strange things that can happen in stormwater, as well as debris and all those things that can happen to tear your cables out. All right, so let's take a look at some of the challenges with traditional flow sensors. You're going to have this rooster tail effect over the sensor. So pretty much water is going to hit it, fly over the top of it. So it's like a cocoon effect. What will happen in that case too is it will read lower level. So one common thing people will do is they will take a standard area velocity sensor, they'll zero it in air, put it in a pipe, and if that water velocity is pretty high, and I'm talking typically anything over about 3 to 4 feet per second, you're going to have a effect on the level. So it's going to read a little bit low. It's also very difficult to calibrate when you have high velocity. And those of you that have installed and calibrated, you know it better than me. You stick a ruler in the high velocity site, good luck getting a good accurate reading. Velocity can also be nearsighted. And what happens is the particles coming at the sensor are coming so fast that it can kind of get a little bit overwhelmed and be a little more nearsighted. And that's due to the noise in the water hydraulics. Difficult to install a mounting band. Anything greater than 3 feet per second from the people I've talked to have said that is almost impossible thing to do. So it's impossible, difficult, and very dangerous. Here's a picture I thought was gave you a pretty good idea of just how a sensor will affect hydraulics, especially at a low level. Okay, here's another picture of a site where they had a standard AV sensor in there. You can see upstream the hydraulics look pretty good. As it got closer to the end of the pipe, we have a couple things going on. We have a lot of turbulence due to something probably on that sensor, or it could be just the ring or the change in the pipe. What happens in this case, we're going to have errors in our level reading, errors in velocity, and the cable is now coming loose from the band due to the high velocity coming at it. You can see it's already catching debris, so that's not a good thing. And it's just not a good application for a in-pipe sensor. So anyway, those are some of the things to keep in mind. Typical applications. We designed really for collection systems initially. Our target was large pipes. We felt that nobody wants to get into a big pipe for obvious reasons, dangerous and just not a good thing. But we're finding over the last couple of years, a lot more small pipes. And we have people using these in, I have them in 4-inch pipes. So they don't need a lot of room or a lot of pipe to work with to be able to get a reading, get a good reading. Okay, low level, high velocity. Here's a good picture of one that was up in Minnesota, and you can see that water is just screaming down the hill, but it's very low level. So all their efforts failed trying to get a area velocity sensor to work there. We will read down, our spec is a 1/2 inch depth to read velocity, although we will read in a lot of cases much lower level velocity. Our maximum velocity is 15 feet per second, so we can go up to a very high velocity. This is the same site now with a laser installed. you should know that the laser can point either direction, into the flow or away from the flow. We don't care. It can also measure reverse or negative flows. Okay, so here's some of the data that we got from the site. You'll notice the velocity up here was 13.2 feet per second on average. And the scale over here on the left, you'll see that's 14 feet per second. So this was one of the highest velocity sites that I've ever been involved with. So incredible how well it did in this location. Okay, so let's talk now on the opposite end, the slow velocity applications. Seeing more and more of these type applications. Anything below a half foot per second can be very difficult to measure. Most AV sensors are going to struggle with that because you get down to now it's so slow, you have noise at the low end and you won't be able to distinguish between that signal to noise ratio. So that can happen with slow water, and it can also happen with very clean water. Why will the laser work here? Well, our signal to noise ratio is incredibly strong, so we are not affected by these types of conditions. We can read extremely low velocity. Our spec is a half foot per second, but we can read in some cases far, far below even our published spec. So here's a good picture of one. You can see the laser dot on the water. And this is a temporary mount. So laser gets its level reading, focuses the laser into the flow. That water is almost like glass. And so with the laser, we don't care what the surface is doing. We're looking below the surface. Here at this location, you can see the dashed line in the second pane is half foot per second. In this case, our point was 0.39 feet per second, so very, very slow. Here's another one that was a wastewater influent. It's a rectangular channel, but you'll see up there, this thing is moving at 0.13 feet per second velocity. So just to crawl, even though it's a fairly large channel, that water was barely moving at night. So nothing else would read that kind of condition, easily anyway. So what do you need to install? How much room do I need to install one? I get this question more and more now, because initially we looked at, okay, you mount it on a wall over an invert in a manhole. Well, we have a lot of people that maybe just have a pipe and they want to measure that. Well, the nice thing about the laser is we don't need a lot to be able to work. So this small opening is really what's all that's required. This is our flow lab at ISCO, and you can see this is some of the cuts that we put in there. They're about 4 inches probably wide by a foot long. And you'll see the laser can, there's the dot on the water in the flow lab. So very easily adaptable. I'll show you a couple of pictures. Here's one where they're doing an industrial monitoring application. They already had the existing pipe in there. So all they did was cut out that opening and away they go. So it looks like this. By comparison, the other option would have been dig that whole thing up, try to put a flume in there, was not going to be an easy solution. So the laser made it very, very easy for them to adapt and get higher accuracy than even with the flume. Here's another one. This is a shrimp facility down south, and this is one they tried to measure flow, or they're trying to measure flow here. There was no good solution to doing this. They went ahead with the laser, and you'll notice the cuts in the top, just a simple cut in the top of that PVC pipe, and away they go. So you want to keep that as far away from the drawdown at the outlet, but they're getting very, very good data from this location. So easily adaptable to some of these conditions. There's another one. This is one in Las Vegas, and that one was in a manhole environment, but you can see at some time they had cut the top part of that pipe out. There was no easy way to get in there to put a sensor on a ring end. So the laser was very, very useful for them. 2 bolts, they drilled it into the wall, and they're in and out of there within probably 45 minutes to an hour. Wastewater treatment plant effluent. So here's another one. A little bit of foam on this one, but the laser can handle quite a bit of bad conditions, and I'll show you one here in a minute. This is one that I have a video on. They're trying to measure this one. This is effluent of a wastewater plant. That's a 2-foot wide rectangular channel. Water's dumping into it, and then it flows down that, and you can see how turbulent the flow is, and you can see also the amount of foam on that in that line. So not an easy place to measure. But this is how they installed the lasers. They went in, they put a homemade bracket across there, lasers mounted over that channel. So initially we put that in, and the customer asked, is it going to work? We honestly didn't know how well due to the amount of turbulence and foam, but it was like, let's go ahead and let's put one in and see. Initially, what we found is data that looked like this. We had drops in the velocity, and they weren't dropping to zero, but they were dropping down to a very low velocity. So trying to figure out, why is this? Why is this happening? Is there anything we can do to make it work? Otherwise, you were going to have to go through some pretty extensive reconstruction, put in some flow straighteners and baffles and all kinds of stuff. So we looked at it, and here is the diagnostic that we got back from this site. And you remember the other one I showed you, it was a very nice, clean one. This is not so clean. And the reason is we're getting low frequency, low velocity on the far left of the spectrum. And really what we want to see is this. This is our real velocity over here. So with the laser now, we've been able to make some adjustments so we can actually, for lack of a better word, tweak it in to say ignore anything left of whatever velocity it is we want. So that's what we did in this one. We just told it, hey, we're seeing these low frequency velocities, probably due to entrained air, big air bubbles on the top, could be turbulence, swirling, and all that. But we went ahead and we set the laser so that we could ignore that. And this is what the data looked like before and after. So before that, which is where the red line is, not so good data, and definitely not anything that you'd want to write home about. But to the right, the data, once we made that change, looks phenomenal. So again, save the customer a lot of time and a lot of money and a lot of pain and suffering just by making a quick adjustment on that laser. So here's a UV disinfection channel, and this one is another one we're becoming more and more popular. People want to measure this, and in the past, the way they do it is you have a moving weir gate at the end, and you try to kind of assume some flows based on the gate position. But now we're finding more and more people want more accuracy in that so they can dose or pace their lights correctly, and the laser now is used in some of these channels. Here's another one that's a high velocity rectangular channel, which was difficult, almost impossible to get into, and some adjustments on some settings, and we were able to get it to read this, which is incredibly difficult. The install on this site was very easy. They just took a Sawzall, cut in a nice little opening in the top of their grating, and the laser just sits right on there, and away you go. So an easy install for them. Here's a challenging one. The water drops basically into this pit. So the original standard laser that we released was not going to work because it was going to read the level down where that foam is and try to focus the laser pretty much below the pipe a couple feet. So that wasn't going to work. So what we did is we made some changes to the laser and some enhancements. So you can order a laser with a built-in ultrasonic or what we call remote ultrasonic. What the remote ultrasonic does is it's mounted on a bracket, typically horizontally, and it deflects off the bracket. Now it measures flow or level and velocity in the exact same location. So this does a couple things for you. One, it will allow you to read in these kind of locations, but two, it will also improve your flow measurement method. And what I mean by that is your best flow calculation will be when you read the level and the velocity at the exact same location, and this accomplishes that. Remote ultrasonic, here's one. This is the influent to a wastewater plant. So what you can see here is water's kind of dumping into this pit, and we have a remote ultrasonic up inside that pipe. So now it's adapting to that change in hydraulics. This is a combined sewer overflow outfall. You'll notice there's a drop coming into that channel, just a couple inch, but it's enough where we would read level here. We would not work because we would try to read velocity. We would try to focus below the pipe, so that wasn't going to cut it. So they put a remote ultra in there. Now we're reading level and velocity in the exact same location. So much better method of reading the flow. Okay, more and more applications kind of like this. This is actually not a horrible one. We'll see a lot that are worse than this, and you'll have bends coming into from the pipe coming through the invert. You might get a 90-degree bend in there. Well, the laser needs to see the level in order to be able to know where to focus. If the level is in such a way that it's hitting the bench, that isn't going to work. So what we're able to do is take that remote ultrasonic, and you can mount that on the wall over your incoming line, and then we don't care really where the laser is sitting because it's going to focus into that pipe coming in. So now we're able to adapt to really, really bad conditions in the manhole. Okay, river applications. We're seeing more and more of these. Typically, they're high velocity. They can go from very low flow or no flow to raging rapids during storm events. You have sensor cables that are in there in the traditional way, which are not good. The only way around that was to put in an ultrasonic to read level, but then you have level only, so you don't have a lot of accuracy there. Benefit of the laser is it can read the slow flow, it can read the low flow, and it can easily adapt to high flow conditions. So it can go from a trickle, nothing in the water to see, so not a lot of particles. It's going to be accurate through the entire range of the event. So again, 1/10 of an inch all the way up to pretty much full pipe or full channel. Here's a good shot of how they mounted one. So we'll get a lot of questions like this: how do you mount one on a bridge or in an open structure like this? Well, you're going to have to get a little creative. We provide the U-channel bracket for the laser, but as far as how you mount that U-channel, you might have to do some manual configuration of your own. The key here is you want the laser supported in such a way that it's not waving in the wind. It's got to be stable. So here's one that was a large channel where they're trying to measure that flow. The laser is not going to see the entire width of that, but the flow is fairly uniform, so they were okay with mounting it how they did. This really is a nice looking application, a nice looking installation. They mounted a U-channel bracket or an L-shaped channel bracket coming out to the side. They have a stainless steel support cable on the back to kind of help keep it from vibrating around. So this might give you some ideas on when you look at how am I going to install one of these. This is really what you need to do. But again, the XY axis on the laser is going to tell you if you're installed correctly or not. Large wide channels. This is in California, so normally they have no flow, but when they get a lot of flow, that whole channel will fill up. They will measure using a laser into this. They would not want to be in this location. They would want to be upstream from that probably. But they can do level to area data points. So you can do level to flow, but you can also do level to area. My level is 2 feet, my area is X. And then you use the velocity of the laser to calculate the flow. I apologize for this picture, but this is one where a laser did go underwater. You can see the chain. They know it's going to occasionally. The laser is rated 6 feet, 72 hours submergence. We have seen in much, much worse conditions than that. So what does the laser do when it goes underwater? Well, it has a built-in continuous wave Doppler sensor that is on the bottom of the laser, mounted upside down. It uses continuous wave Doppler to measure the velocity and a pressure transducer to measure the level. So now you're going to get very accurate level measurement, and you're going to get very accurate velocity when that pipe goes full. And the reason is because of peak velocity, or the highest velocity, is typically towards the top. The way the AV sensor is mounted on this, we are now going to be looking in the right location for that velocity. So the results when it transitions over from laser to the area velocity have been really, really very, very impressive. Also, it should be noted that we can store one flow rate that will automatically switch from laser to the AV sensor during this condition. So when you graph your data or you send it 4 to 20 to a SCADA, you'll have one continuous flow reading that will be representative of whichever technology you decided to use. Okay, let's talk stormwater a little bit. Stormwater is another big one that we're seeing. This is a very colorful location, but that means there's probably a lot of kids down in there, and nobody wanted to put something that could be vandalized. So they wanted to go with a laser up into that box culvert where they have the gates. So stormwater, another stormwater laser application. This one was kind of a challenging one, but it was very easy to retrofit. They're in a secure location, so they weren't worried about vandalism. They used a U-channel C-clamp actually to mount the laser bracket in that pipe. So pretty interesting. The guys are very creative on how they install that. This one I call extreme stormwater. This was some stuff done on the East Coast with USGS, and you can see there's very, very little flow in that. So putting a standard area velocity sensor was going to give them no baseline flow that would be worth anything. That was something that was important to the customer. So we went ahead, they put a laser in. It's very clean water, and it's low and it's slow. So it's down to, in this case, about 1/10 of an inch, moving at less than 0.2 feet per second. And the laser's reading that flow. So it's incredible of what it's able to read. And here's some of the data from that site. So you'll see they had a couple storm events. Everything picked up fine. But when they did not have a storm, on the line that I have indicated there, the level was 0.88, so less than an inch deep, and it was 0.25 feet per second. So incredibly slow velocity, challenging at best location. All right, so let's talk equipment options real quick, and then we'll be close to wrapping up. You have to decide how you're going to power this device. Do we have AC or DC power? We can power off of either one. A lot of solar charging systems are going in as well, so keep that in mind. You can do that with those, but if you're going to go with a permanent location, most of the time you'll go with a signature meter. If you go portable, you can either use a portable signature, or you can use the 2160, which is the blue box battery powered unit. These are, again, very similar to a 2150. They program almost identical. So the learning curve, if you have 2150s, to adapt to a 2160 is a piece of cake. So pretty good way to do that. So let's talk a little bit about the signature. The signature is our main platform we call a smart device. It uses what's called TINET, Teledyne ISCO Environmental Network. All our sensors now are, quote, smart sensors in that they are plug and play. So you can plug technically 9 sensors into the signature. It will scan for those and it knows what it is. Oh, you're a ultrasonic. Oh, you're a laser. So very, very smart. In the old days, you plugged and played with different types of electronic circuit boards. In this case, you could buy one signature, and if your conditions change or you need something different, you can just buy a sensor, plug it in, scan for it, and away you go. You'll see there's a lot of outputs there, internet, alarms. You can download using USB, FlowLink, Modbus, SCADA outputs, Ethernet, as well as 4 to 20 milliamp, and of course, cellular. So where we're seeing a lot of push lately is industrial pretreatment monitoring. So any industry, really, the last thing they want to do is have to measure flow. So what the signature does for them is the signature is able to make it quite easy. It's a really good solution. It's also very flexible if they have non-ISCO flow meters. So if they have a magnetic flow meter out there and they're comfortable with what it's doing, and it has Modbus or analog output, we can take that right into the signature and we can store that data. We can also transmit that data. So good way to work with other technologies. A single meter with multiple technologies. Again, it's easy to upgrade. You don't have to send anything back to the factory. If you have a FlowLink Pro database, this allows for the modems on these meters to push. So we have a customer down south that has their collection system on FlowLink Pro. They're doing their normal day-to-day flow monitoring using 2150 area velocities, lasers. That data is going to a FlowLink Pro database on the city server. Well, now they decided to go ahead and capitalize on that, so they're using signature flow meters on their industry, which allows the industry to be consistent. So they have one platform, but they can modify it as they need. They have a flume that's working, great. They put a ultrasonic signature in and a modem, and it transmits data now to the city's database. So the industry doesn't have to worry about anything. But the other neat thing about this is they can get immediate alarming and notification if there is a problem at the industrial site. So these guys can see, I have an alarm condition. They get it on their phone, they pull up FlowLink Global, and they can immediately see what's happening. This is FlowLink Global. What FlowLink Global looks like is FlowLink is Global is the web platform. So they just log in. Once they log in, they get an immediate, what they call dashboard. Dashboard is going to give them immediate notification or identification of what's going on in their system. Green means all's well, yellow means the meter didn't call in, and red means I have a hard alarm. A hard alarm can be anything that the meter's programmed for, whatever it reads. So you could say velocity, Doppler power is low. You could say high level, flow rate, battery voltage, and any of those things. So this gives them a quick view. The graph, one click of the button, and you're going to get a graph up. It is not the most detailed analysis tool, but you can export it, put it in Excel, or you can bring it right into FlowLink. The GIS mapping is very useful as well. So now you can look at a big grid of your collection system and see what's going on with the colored indicators. Okay, so why does the laser work in these applications? Well, it's a non-contact, so it's not going to get covered. Uses an ultrasonic sensor that doesn't drift and not affected by wetted hydraulics over wetted sensors like we showed you. Remote ultrasonic is key because now we can put it at the exact same point that we're measuring velocity to improve accuracy. The laser measurement technique is pretty incredible. The signal to noise ratio is phenomenal, and that helps us, again, really pick into very difficult applications. We take 5,000 velocity measurements per point. Again, we do that in a very quick, short amount of time, 2 to 3 seconds. So pump station applications, we use them in those all the time. Up to 15 velocity points. So again, 75,000 velocity readings. If it's a billing location, you have AC power, you can run all 15 and get the most representative sampling of your velocity and your flow in that channel. So to wrap this up, laser is really the most advanced open and versatile open channel flow meter available on the market today. Works in applications where people couldn't measure before, and now they're trying to measure this stuff. So it's amazing to me the amount of applications that have popped up that people didn't even try to measure before, and now they can measure with the laser. The accuracy is also something that is continues to amaze everyone, including us, is how accurate it is under high and low velocity conditions. So it's able to read accurately through a wide range of stuff. And when you have great data like that, it's also, again, very nice to be able to pull up that data on the internet. So with that, I'm going to turn it over to some questions.
Okay, and as we get ready to answer questions, I just want to let everybody know that this webinar is being recorded and will be available for all attendees later on this week. It'll be sent out to all registrants and attendees. It will also be available on our YouTube channel where you can find all previous water webinars. Also look out for communication on next month's webinar. Next month we'll focus on the AccuLink. So be on the lookout for an email with more information on that upcoming December webinar. So we have quite a few questions that we can go through.
Okay, I'll go ahead and address the first one here. It says, do I need to clean my laser after every time it goes underwater or becomes submerged? That's a good question, and that's one thing where when you look at what you get back, the laser goes underwater, and we, believe it or not, had some that have been under 28 feet of water recently, and water level comes back down. The customer says, wow, do I need to do anything? Well, two things you want to look at. One would be that Doppler diagnostic. Am I getting anything back? Did my X-Y axis change? Did anything shift? If all that looks good, that means your laser mount physically didn't move. And if I have a good return Doppler signal and my Doppler power is good, that means nothing got up in that unit. The laser housing is designed like a diver bell. So it's designed to, just like you took a cup and you stuck it upside down in a sink full of water. It should hold that water tightness and keep that out of there. So anyway, that's a good way to know, do I need to do anything? Most of the time you don't. Okay. All right, let's see. Okay. Can you go over how the fixed high noise in situations where high velocity and turbulence affect the results, like the example square wastewater effluent? Okay, so what will happen is if you have a turbulent channel and water's going every which way, what will happen is you'll see it in the diagnostic. You'll see that spectrum. A lot of those velocity returns don't agree. So you'll see the signal reduce, but what will happen is you will get, as long as it's higher than 1,000, again, Doppler power, that means it picked out enough that it considered to be good. So you will see it in the data, but the laser will actually, there's a couple other advanced settings that you can put in there that will compensate for those as well. So we have them in some very, very nasty locations. Having said that, it is not going to, you want to give it its best chance and, give it the, best hydraulics you can if possible. Okay. Another question is, what's the maximum height the laser can be mounted over the flow and still get accurate readings? The laser doesn't care really how high above the flow it is. It will give you accurate data all the way through. If you're 10 feet above it, it doesn't matter if you're 10 feet or 2 feet above it. So the focus point or that converging section changes a little as it gets longer, but or as the distance gets longer, but it's still going to accurately record and repeat and read those velocities on that. So yeah, a lot of them are in very big pipes with very low levels and should not affect it. Okay, let's see. Channel. Okay, power. That's a good question. So what are we looking for battery life? With the standard laser with just one battery module, in the case of a 2160, which is the blue box, you're going to get roughly 12 weeks if you have good batteries in there with no modem and you're doing 15-minute readings. What we're seeing a lot now are applications where people want to run it for longer without touching it, because it's nice if you have a good design that you don't have to service. Well, it'd be nice to not change batteries. So deep cycle batteries are also becoming extremely popular. Yes, they're a little bit heavy when you put them down in the manhole, but you can hang them at the top. As long as you can do that, you're going to, not have to service these things. We have some sites where they're very, very difficult locations. They are high traffic, safety concerns, and so on. And they now go out and they're doing 5-minute readings with the cell modem. With the deep cycle battery, they'll go out about every 4 months and change it. So they don't really have to service anything, and they just change that battery and get out of there. So deep cycle batteries are the way to go. I will also tell you they're not all the same, so you got to be a little bit careful with that. I'll have people say I used a deep cycle battery and that lasted 2 weeks. Well, I find out it's a motorcycle battery. It's not really a deep cycle battery. So not all of them are, again, created equal. So be a little bit careful on that. Okay, just got a lot of questions, which is great. Okay, let's see here. Okay, for large pipes and channels, does the laser velocity reading account for where it is located in the velocity profile, or does it simply average its reading? Same question for the continuous wave. How many inches below the water does the laser read? The laser is looking for the peak velocity. So what we're doing on that is we are, as the water level changes, we go deeper into the flow to get the peak velocity. As far as the distance goes in there, I'm not 100% sure exactly how deep it goes, but a continuous wave sensor on the bottom, what that thing is doing is that's transmitting up to the water through the water column, but the trajectory or the angle of that velocity sensor is fairly flat so that it can handle low level velocity. So in our experience, a continuous wave sensor, when it gets above roughly 1.5 to 2 feet, your velocity will start underestimating because that peak is following the surface as it goes towards the top. or as the water increases. So you will have some errors in that, and that's why sometimes when people use them in standard AV sensor in a 96-inch pipe, yeah, when it goes half full or more, you're going to be low on velocity. That would be the reason why you would use a pulse Doppler or ADFM, the acoustic Doppler flow meter. That one will do a complete profile. The laser is another good way to go. It does not profile a complete profile like the ADFM. So if you have an application where it's maybe a large channel and I have a 2-foot weir wall in the bottom of it and my level is 6 feet, the laser doesn't know that you have a weir wall in there. So it's not going to work in every single application, and that's where the other technologies might be better one to use for that. Okay, so what's the limit in size for the laser sensor as far as channels and pipes go? We have lasers that are in, like I said, one down in Kansas. It's influential water plant, 20-foot wide channel. The laser reads roughly a loaf of bread, is kind of the way I describe it. So in a 20-foot channel, it is not going to see the entire 20-foot channel. So the question is, how uniform are the hydraulics and how uniform is the flow? If you could mount one in the middle of that channel and your flow is fairly uniform, you should be pretty good. If it's not, in the case of the water plant, they actually suck water off of each side of that channel depending on what they're doing. So the water velocity can be different on one half of that 20-foot versus the other. So in that case, they went ahead and they used 2 lasers on one signature flow meter. So that was a very good way to do that. Okay. All right. How often do you have to check instrument calibration? That's a good question. Yearly checks are required for NPDES compliance. The laser measures the distance to the water. That's a non-adjustable setting. It has to know the distance in order to know where to focus. So that's part of the software or firmware inside the unit itself. When you know the distance, so a really neat thing about calibrating the laser is that you could do the standard ruler method, stick a ruler in a pipe and try to calculate the level that way. But if you can measure from the bottom of the laser to the bottom of the channel, let's say that's 6 feet, and then you let the laser read it, the ultrasonic says I'm 4 feet to the water, you know your level remaining is 2 feet. So you can do the math that way. What's nice about that is once you get that distance value, it's a whole lot easier to read a ruler at the bottom of the laser than it is sticking, your face down by the flow. So a good way to do that. That's also a great way to post-check your data as you go down the road to make sure nothing drifted. So that's a very useful thing for level. Velocity is a little trickier because what we have would be for velocity, the diagnostics that I can look at or you can look at and say, yep, this thing is looking great. I have no, the laser velocity will not drift or shift or change. It will either read or it won't read. So no great way to verify that except people will use handheld velocity sensors and put them in the flow and do kind of a velocity profile. And that's okay. That's okay to get kind of a sanity check, but when it comes down to it, the laser, as far as what it reads, nothing's going to read more accurate velocity than what that thing reads. But people will do a hand check to make sure it's reasonably close to what they think it should be. Now, the other thing that we can do is we'll have people that have a number of these lasers, and they can send it back to the factory yearly if they want. We can run it through its paces and give it its clean bill of health. We run it through a calibration facility and double check all that. But the other thing you might consider is if you have a few more than a couple of these, you may want either a master unit or a spare unit. If you had a master laser, you could send that back every 6 months. We could run it through its cal checks or once a year. And then when you go out to the field, you could pop one out, pop another one in, make sure it reads what the other one did, and just put your other one back in if it matches. And if it doesn't, you could send it in and we could check it out. So again, good ways of verifying that everything's working fine.
I think we have time for one more question here. And just a reminder, if you have more questions or you want to follow up afterwards, Rick's contact information is on the screen right now. So we'll answer one more question here and then we'll wrap up.
Okay, let's see. Okay, laser sensor, what's the expected service life of the laser? Laser's been out since 2013. We design, like any ISCO product, to last as long as possible. That's a very difficult thing to quantify, but we've done a lot of life tests and things like that. We expect at least 10 years, before you have any major, hopefully major issue. Our warranty's 1 year, but we design for at least 10 years of life. I can tell you we've had lasers that were in locations where they did not use the stainless steel mounting bolts. The laser was dangling by a cable hanging into a stormwater line for 4 months, just getting slammed around every time it rained. They pulled it out. There was the side-to-side servo was not working right, but they were only using the same single middle point anyway. And once they cleaned it up, they put it back in service and it worked. So that's incredible that it's able to withstand that. So the laser is incredibly rugged. And again, on the lines of everything that Teledyne ISCO manufactures, we design for long term. And I think those of you that have used us for a while understand that. So we'll see as we go. We've been out now for over 5 years and we have units. They're literally serial number 1 that's still in use and they've never touched it. So.
Great. Well, thank you, Rick, for all the wonderful information today. And thank you to everyone for attending this morning's webinar. Again, this will be available to all attendees later on this week, and you will receive an email with a link to the webinar. Also, please be on the lookout for our upcoming December webinar. That will be focused on the AccuLink, and information should be going out to everyone within the next week or so. So thank you so much to everyone for joining us today, and have a great day.
Thank you.